Hello and welcome back to my Physics Online video lectures series. Today's video we're going to look at 2- and 3-dimensional kinematics, or as we might say, kinematics in more than one dimension. And the point of all this is that so far in the lecture set we've seen kinematics in straight line motion, so 1D kinematics, and then we've looked at a little bit about properties of vectors, and so now I think we're ready to move on to talking about what happens when you actually have to use vectors that are 2 or 3 dimensions to describe the motion of an object. And so here you have the multi-shot picture of a snowboarder who's jumping, and he basically leaves the ground here, and you can see describes what looks like a parabolic arc. And throughout this motion, he has a constant acceleration straight downward of g, or about 9.8 meters per second squared. And so we're going to look at how to describe this motion, how to describe him as a projectile, which basically means that he has movement under only the influence of free fall. I suppose you could add air resistance, although I'm not going to do that just yet. And so we're going to be looking at projectile motion, and we're going to be looking at trajectories, which is a trajectory is basically the path that an object in free fall motion takes. And so in the case of that snowboarder, or in the case of this shell that's being launched from the battleship, once it is projected into the air, so once the snowboarder jumps and leaves the ground, once the shell has left the barrel of the cannon, then the only thing that is really influencing it is gravity, and maybe to a lesser extent some air resistance. And so at this point we have a projectile. So the vector terms in 2 dimensions might be described as such. So your position vector you might put in Cartesian coordinates using x, y, or you could put them in polar coordinates using r, theta. Or if you want to use component form, you might use xi hat plus yj hat to represent the position of the object. And then displacement, velocity, and acceleration all have similar definitions to their previous definitions. Namely, the displacement is always the change in position. The velocity is the rate change in position, or in other words is the displacement per unit time. And the acceleration is the rate change in velocity. But this is now all happening in 2 dimensions. So your velocity vector might look like vx, vy, or vx I hat plus vy j hat. And in polar, that would be v, theta v. And of course you can go from 2 dimensions to 3 dimensions by essentially adding a third coordinate, or by adding a third unit vector. So you can go x, y, z, or xi hat, yj hat, zk hat. But you can also use spherical coordinates, which make use of total distance between origin and object, and then your polar angle and your azimuthal angle. Or you can use the cylindrical coordinates, which use the polar distance r and the polar angle theta, and then how high above the polar plane the object is, z. So in 2 dimensions, what happens is this. Position is basically telling us where the object's located with respect to the origin, same as in 1 dimension, same actually as in 3 dimensions. But now in 2 dimensions there's basically 2 ways to specify it. One is that you could use cardinal distances, such as 40 meters, negative 30 meters, or 40 meters to the east and 30 meters south, or you could say 40 meters I hat minus 30 meters j hat. And so those are your cardinal distances. Your other option is to use distance and direction, which is sort of equivalent to saying that an object is 50 meters and 60 degrees or 63 degrees away from me. So that could be 63 angles elevation above the horizontal, or maybe you're using a compass, in which case this is 63 degrees north of west, which normally you might actually say is 27 degrees, 63 degrees north of east, which you might call 27 degrees east of north if you were using a compass. So what the polar coordinates are telling us is basically how far away we are from a reference point and which direction. And you could think of this by analogy as you're in a city and you're trying to get from your start point to your finish point, your starting point to your destination. The polar coordinates are analogous to what you would do if you had a helicopter and could take a straight line path. But if you're actually on foot or driving, you might have to follow the streets and therefore go along city blocks. And so your Cartesian coordinates are basically saying how many blocks over and how many blocks up are you going to have to go to get where you're trying to go. You can think of displacement again as the change in position of an object. So delta r is always the final minus the initial positions. And so the displacement from point P to point Q is the position of point Q with respect to the origin minus the position of point P with respect to the origin. And basically this lets us start at some point that's not the origin and also end at some point that's not the origin. This is basically going to be analogous to considering the second vector when you're adding two vectors together. Namely, you're adding r plus delta r and you're ending up with r final. So r initial plus delta r equals r final, and this drawing is consistent with that. If you wanted to add r initial to delta r, you'd start at the origin, end at the end of r initial, and then start there and draw out delta r, and the end of that delta r gives you r final. The origin might be a particular agreed upon reference point, or it might be, for example, the position of an observer who's watching this motion happen, usually of a stationary observer, although you can also do this with relative motions, which is a topic for another lecture. So in 3D, again, there are three ways that we can go about specifying a position, and they're sort of all drawn here in this figure 4.1.4. And you can do it in Cartesian, which is x comma y comma z, or using unit vectors, you have x I hat plus y j hat plus z k hat, where x, y, and z are all functions of time. So looking at this system, you have a set of axes, so x-axis, y-axis, and z-axis, and your point P is right here. Point P can be projected downward into the xy plane, and it has an x and it has a y value. And then there's also a z value, which tells us how high above the plane is it. So this length right here represents x, this length right here represents y, this length right here represents z. Lest you be a little confused by this diagram, this x is representing this distance, but this value x of t could also be the projection onto the x-axis. So x of t has this value along the x-axis. Y of t is this distance and has this value on the y-axis, and so on. The second option is to, instead of using Cartesian or basically rectangular coordinates, is to imagine a cylindrical coordinate system. So if that's done, you need to have a distance from the XYZ origin point to the projection of your point in your XY plane. So this is basically a polar distance because this could be thought of as the polar plane. The XY plane could be the polar plane. So this red line right here has a distance little r of t. And the angle right here between the x-axis and this red line is theta of t. And then z of t retains the same definition as before. Third option is to use spherical coordinates, in which case what we care about is the absolute distance from the origin to the point, so that's big R of t, and then we care still about the polar angle theta of t, and now we use the azimuthal angle phi of t, is the angle between the z-axis and this position vector. So the purple thick arrow is actually the position vector in all three cases, and it can be broken up into xyz or r theta z or r theta phi, depending upon which coordinate system you want to use. Okay, now let's consider velocity also in 3 dimensions. So we'll start off by considering this in Cartesian coordinates. So what is the velocity? It is the displacement per unit time. So instantaneously, that looks like the derivative of position with respect to time, if you imagine the position to have some particular function that goes with it. And this derivative, we basically can apply piecewise to the position equation. So recall that the position is x of t I hat plus y of t j hat plus z of t k hat. So the velocity vector, you apply this derivative, you end up with dx by dt I hat plus dy by dt j hat plus dz by dt k hat. And so we call these v sub x, v sub y, and v sub z. So you can separate this easily into individual dimensions, each of which might end up looking like a 1D motion. In any case, what we do from there is we could also have spherical coordinates, and for that matter we could also use cylindrical coordinates and also obtain the velocity vector. But in spherical, when you go piecewise, what you end up with is dr dt r hat. In other words, how far away is this thing moving with respect to the center, times d theta dt and d phi dt, both of which are essentially rotational terms. So one would be more or less what is the rate of orbit in only the xy plane. The other one is more or less what is the rate of orbit perpendicular to that xy plane. So the main one that we'll probably be using in this class in 3 dimensions is Cartesian, but in other courses you may find that it's more convenient to use the other forms. So returning from 3D back to 2D, we could ask, what is it that the velocity components are actually trying to tell us? The answer is that in polar, the magnitude is telling us the object's total speed, and then the direction is telling us which way the object is actually heading. And if you switch instead to Cartesian, it basically is telling you how quickly along each of the 2 cardinal directions your object is traveling. In other words, how quickly is it rising or falling, and maybe how quickly is it moving forward or backwards. Alternatively, how quickly is it going left or right, and how quickly is it going forward backwards. Now the signs in the Cartesian actually are telling us whether the thing is moving forward or in reverse, and whether it's rising or falling. So usually forward means greater than 0 for x, reverse means less than 0 for x, rising is greater than 0 for y, falling is less than 0 for vy. And alternatively, if you're using a map and this thing is just walking around on the ground, then usually x goes with east or west and y goes with north or south. So we can break up Cartesian coordinates into individual 1D motions. This right here actually is showing the motion of two objects. The first object is one which sort of rolls off the table with an initial horizontal velocity, and the second is one that is dropped from the exact same height, released with no initial velocity. And you could think of these dots as if you had maybe a multi-shot photo of maybe the dot is a ball. Then what's happening is maybe once every second or once every fraction of a second, more likely, you get a picture. So for example, these these 5 dots are showing the position versus time at 0, 0.1, 0.2, 0.3, and 0.4 seconds of this thing's having fallen. And this right here might be showing the position at 0, 0.1, 0.2, 0.3, and 0.4 seconds of having projected off of this tabletop. So that's what the red dot is showing. And you'll notice that the red dot at same time interval is at the same height in all cases. So I could draw a horizontal line and it would always be able to pass through one dot and the equivalent time position dot for the one that just fell and the one that was sort of pushed off. So that's what the red dots are showing. What the green arrows are showing is actually the velocity at each of these times. So for the one that's just falling, there's no initial velocity, and for the one that was projected, there's an initial horizontal velocity. And after having fallen, this one has a little bit of velocity downward. This one right here still has a horizontal velocity and still has the same downward velocity. So the net velocity is actually the vector sum of those two components. And what you'll notice is that the horizontal velocity vector remains the same in all 5 of these sequences, and that if you compare the vertical velocity from one to the other, it's always the same length. Okay, so now we can consider what is the acceleration in 2 dimensions. So in polar, the magnitude is telling us the object's total acceleration. So basically the total change in speed per unit time if only this thing is not turning, or more accurately, it's telling us the total change in velocity per unit time, because again, the change in speed is not necessarily going to be equal to the change in velocity. In fact, you can have an object which has no change in speed but does have a change in velocity because the object's turning. That happens, in fact, in uniform circular motion. So that is what the magnitude is telling us. The direction basically tells us which way the object is actually accelerating in. And we'll get a little bit more into what causes acceleration in the next lecture set when we talk about dynamics. If the acceleration is not in the same direction, or else 180 degrees opposite direction as the velocity, then the problem has to be treated in 2 dimensions. If the acceleration and the velocity are in the same direction, you can usually approximate the problem as a one-dimensional problem just by calling that one dimension the dimension along which both the velocity and acceleration point. You only then have to have a two-dimensional problem if you're insisting upon using a reference point or an observer which is not along that line. However, if there is an angle of other than 0 or 180 degrees between acceleration and velocity, then the problem must become at least a two-dimensional problem. In Cartesian, basically what the signs are doing is they're telling us how much each component in the velocity vector can change per unit time. And so, again, if you want to get the acceleration, you basically take the time derivative of the velocity vector, or you take the rate change in velocity. So what all of this means is if you break up the motion into its Cartesian coordinates, then each Cartesian direction, or each cardinal direction, can be used to represent an individual motion, basically that is in one dimension. So, for example, that means that the x component of acceleration should only affect the x component of velocity, which in turn should only affect the x part of the position. And then the y component of acceleration affects only the y component of velocity and the y component of position. In other words, the x part of velocity does not affect the y part of position, and vice versa. So that is part of what was shown on that previous diagram that showed the little red dot with the green arrows. It also implies such things as that if you have a setup like this where there's a little ball that is tied to some string and then tied to the end of a spring, such that when this snaps, the ball falls and this ball is launched, then these two objects actually will have, if they initially had the same height, they will have the same height at all points until they collide. So basically in vector form we might write something like position versus time looks like r equals 1/2 at squared plus v initial t plus r initial, where r, a, v, and r initial are all vectors. So this is actually the same equation, and again we're assuming a constant acceleration. This is the same equation that we used in 1D motion. It's just that now each of these maybe has 2 or 3 components to it. And likewise for velocity versus time, the change in speed versus acceleration and distance equation looks a little bit different in that you end up using dot products to keep track of the vector form of everything. But you could in principle apply it. So what does this actually look like in 2D in using vector notation? And again, if you want to go 3D, you're basically adding an additional term with a k hat. The answer is that you can break up in 2 dimensions the position vector into x and y of t. So x of t I hat, y of t j hat. And so x of t basically looks like 1/2 ax squared, 1/2 ax t squared plus v initial x times t plus x initial. So all of that is times the I hat part. And then likewise, you can have for the y part 1/2 ay t squared plus v initial y t plus y initial times the j hat. And if you wanted to get the velocity versus time, you'd have ax t plus v initial x I hat plus ay t plus v initial y j hat. So again, these can now be broken into 2 sets of equations, or if you have 3 dimensions, you can break it into 3 sets of equations. And each set basically represents one one-dimensional motion. They end up being coupled because they all share this one parameter, time. But other than that fact, you have the same equations that you've already been dealing with in one-dimensional motion. So what does a projectile motion look like with diagrams? Well, you've seen a simple version of it. That was the one with the red dot being projected off the table horizontally. Another form of projectile motion involves having basically an initial velocity that is not only in the horizontal direction. And so that initial velocity vector gives you the initial angle of launch, and it can be broken into y and into x. And what you see here is that the velocity vector is changing. The y part of the velocity vector is changing. The x part is basically staying constant. The x part is staying constant because we're assuming that the only acceleration is the free fall acceleration, which is straight downward. Again, if we had air resistance, then there might also be an acceleration from that along the x direction, and so you'd see a change in the x as well as the y components of velocity. But in the case of negligible air resistance, v0x or v initial x is equal to vx at all points in the object's motion. I want to work through an example of all of this now, of a motion that is in 2 dimensions. So you have an object that begins at the origin with some velocity and some acceleration, and we want to know where its position and velocity will be after 5 seconds. Okay, the first thing that we should do here is write down what we know. So this would include the initial position, the initial velocity, and the acceleration, which is constant. Our next step then is to actually combine these things to figure out what the position will be. So basically the position is 1/2 at squared plus v initial t plus r initial. And so you can break that up into the x part and into the y part. So the x part basically ends up having something along the lines of 1/2 times this 1.00 or 1.0, excuse me, meters per second squared times the time, which is 5.0 seconds squared, and then the other two terms actually are both zeros here. And similarly, this term is 0 and this term is 0. So you end up with basically 1/2 times 25, or 12.5 meters in the I hat direction, and then in the j hat direction you have so plus 1.0 meters per second times 5 seconds times j hat, which this right here is 5.0 meters j hat. So your final position therefore ends up being 12.5 meters I hat plus 5.0 meters j hat. We can, of course, change this from our polar to being in change it from Cartesian to being in polar by basically squaring these two terms and adding them together and taking a square root, and then by finding the angle. I leave that as an exercise to the interested viewer. The other part of this question is, what's the velocity after 5 seconds? In this case, you use the velocity equation, which basically says that the velocity should be the acceleration times the time plus the initial velocity. So the acceleration again is 1 I hat plus 0 j hat, and so we would end up with 1 times 5, or 5 meters per second in the I hat direction, and then in the j hat direction we have 1 meter per second plus 0 times the time, so 1.0 meters per second in the j hat direction. So if for some reason we wanted to put this into polar, for example, maybe we want to know how far away the object is from where it started, or what the displacement is, distance and direction from its initial. And if we wanted to know how fast it was going in which direction, then we could convert to polar in the usual way of converting from Cartesian to polar. And then we would basically obtain a result like this: 13 meters away in the 22-degree direction with a speed of 5.1 meters per second in the 11-degree direction. So before moving on to projectile motion per se, I wanted to show a couple of different kinds of graphs that you might encounter when trying to describe the motion of a projectile. So there's the space-time graphs, which might look something like this. So this is showing us how the height above the ground is evolving with time, and also how the distance traveled horizontally, or in other words, the range, is varying with time. You'll see that this one right here is basically a parabola. This one right here actually is more linear. That's because you have an acceleration as well as a non-zero velocity in the z direction, whereas you have only a non-zero velocity and zero acceleration in the range direction. You could also look at it in configuration space, which this is what you'd basically get if you were able to take an actual series of multi-shot photos of the object's motion. So you'd actually see the object trace out this parabola in above the ground. You could also look at things like the momentum versus the relevant axis. This is sometimes called phase space graphs. Those we won't really deal with in this class. Neither are we too terribly interested in hodographs, although you could in principle use that a little in this course, showing how the two velocities are sort of changing with respect to each other. So you see that it's a constant velocity in the x direction, but a changing velocity in the z direction. Be that as it may, what we're interested in doing here is actually trying to describe a projectile's motion. So a projectile itself, you're launching it from some initial position, which might be xi hat plus yj hat, or in these equations x naught and y naught. And you have some initial velocity, which has an x component and a y component. And then you have an acceleration, which is g downward. So basically 0 meters per second squared I hat minus 9.80 meters per second squared j hat. So very often in these problems you're given an angle of elevation and an initial speed, which is essentially the velocity initially in the polar coordinate. And it may be useful to convert first to Cartesian coordinates because ultimately you're often asked to find things like how far away the projectile will land. In other words, what's the range of the projectile? So by way of example, let's consider this howitzer. And so the howitzer is going to fire at an initial angle of elevation 20 degrees and an initial speed of 827 meters per second. So what we want to know is what the maximum height that the shell will attain, how long it'll be in the air, and how far away it will land, and also what happens if we change the angle to 70 degrees. So we're assuming no air resistance for that. So to solve this problem, I have drawn up a short diagram showing what basically is going on in the initial conditions, and I've written up my set of equations here. So what we want to do as our first step is to convert the initial velocity into Cartesian. So to get the x part, you take this magnitude and you multiply it by the cosine of the angle, and you'll get 777 meters per second for this 20-degree angle. For the y part, you use the initial magnitude times the sine of the angle, and you get 283 meters per second. So now that you have that, you can try to get the time of flight, which is the total amount of time that this thing is in the air. And to do that, one way is to get what the maximum, the time to get to that maximum height is, and double it. And so to get to the maximum height, the time required for that is the initial y component of the speed divided by the gravitational acceleration, which is 9.8 meters per second squared. So you do that and you find that it takes about 28.9 seconds to get to the apex of the arc. And so then after that, you can get the total time of flight by multiplying by 2. So 57.7 seconds that it spends in the air. Then you want to get things like the range and the maximum height. So the maximum height, you refer to this equation. This actually is just a one-dimensional equation, so you can plug in the numbers for the time to get to that maximum height, and then for the acceleration, for the initial speed, and for the initial position. What you end up getting is that it attains a maximum height of about 4.09 kilometers. Okay, to get the range, all you have to do is multiply the initial speed times the time of flight, and then add to that the initial position, but the initial position was 0 anyway. And so when you plug in this initial speed for x, 777 meters per second, and this time of flight, 57.7 seconds, you find that it has a total range of about 4.49 kilometers. So the second part of this question was, what happens if everything is changed, or how does everything change if your angle of elevation is 70 rather than 20 degrees? So you do the same process again, but you get slightly different numbers. For example, your initial x speed is now 283 meters per second. Your initial y component is 777 meters per second. This leads to a longer time of flight and time to reach the maximum height. So 79.3 to the maximum height, 159 seconds for the time of flight. And this means that, in fact, it will go a lot higher, actually to 30.8 kilometers. However, and this is the result that I'm most interested in posing this question, you find that the range is still about 4.49 kilometers. So you have the same range at 20 degrees and at 70 degrees. It turns out if you were to plot the range versus the initial launch angle for any speed you choose as a launch speed, what you find is that there is sort of an optimum launch angle to obtain the maximum amount of range. Now this, of course, is assuming that you're ranging across flat level ground with no air resistance. But what you see here is that on these plots, you always end up with a 45-degree angle. And you can get that by basically obtaining this range equation and optimizing it for initial launch angle. So in order to obtain that range equation, by the way, what you do is you begin with your kinematics equation. So for example, y final is 1/2 of the gravitational acceleration times the time squared, and that's downward, plus the initial velocity in the y direction times the time, plus the initial position, which we'll take to be 0. And similarly, you say that x final is the initial velocity in x times the time plus the initial position, which we will also take to be 0. And finally, that when you reach y max, so we'll say y max have v sub y equals 0. And the total time of flight, TOF, is twice the time to get to this condition, T max y. Alright, so now we go through and we basically solve for these things. So this right here, what we're using is that the final v in y is equal to the initial v in y plus the acceleration in y, so basically minus g times the time. So if we want to solve for the maximum time, then this right here becomes 0 and this becomes max y. So T max y again ends up being v y initial over g, and so the time of flight ends up being 2v y initial over g. Okay, so now we can substitute this expression right here into our expression for the range, basically. And what we end up finding is that the range, or the x max, is equal to Vix times 2V IY over G. So this should probably say XI to be consistent. Alright, well, we also remember that V initial for X is equal to the V initial times cosine of theta, and the V initial for Y is equal to V initial times sine of theta. Both of these are theta initials. So this right here basically is going to give us VI cosine theta I times 2VI times sine of theta I divided by G. And then we invoke the trigonometric identity, which says that basically it says that 2 times the sine of any angle, we'll call that angle theta, times the cosine of any angle theta is equal to the sine of twice angle theta. And so if we do that, we see we have a sine theta and a cosine theta and a 2 here. What we end up getting is that the maximum range can be simplified to Vi squared times sine of 2 theta divided by G. And so that's where that equation is coming from. So given that this is the range equation, again, assuming that the initial position is 0, 0, what we can do is figure out when is this equation at a maximum. And the answer is it's at a maximum when sine of 2 times the initial angle is also at a maximum. So what is the maximum value for the sine function? Well, it's 90 degrees. So twice the angle has to be 90 degrees, and therefore the angle should be 45 degrees to maximize the range. Now again, this is not valid if you break this symmetry. In other words, if you were to launch this thing off of a cliff so that it has an initial position that is higher up than, say, the final height is going to be, then you'll find that the maximum range varies a little bit with angle. In fact, the higher up that you launch from, then the smaller is this optimum angle. So here the optimum angle is more nearly maybe 33 or 34 degrees, whereas initially it was 45 degrees when you're launching from across flat ground. So that's all that I wanted to do in today's video. And so hopefully you got a lot out of this video. And I suppose these are basically all the sources that I pulled figures and that kind of thing from. Anything that's not credited in here is something that I made myself. So like figures 4.1.16 and 4.1.17 I generated myself by sort of plotting points. So in any case, that's it for today, and thanks for watching.